Hi, everyone. So I wanted to start on 3D quantum mechanics, but there's one thing I wanted to mention about yesterday's lecture. So we discussed this expression for transmission probability or tunneling probability. It looks pretty messy, but if you look here, the argument of the cinch, this is really L, the width of the barrier, divided by the penetration depth. So when L is much larger than the penetration depth, that factor inside the cinch is very large. And I discussed that you can make L larger than penetration depth either by increasing L and keeping the energy, or you can keep the L and you make the energy smaller so that the penetration depth becomes small. I also discussed that cinch is a combination of growing and decaying exponential. So when this quantity is very large, when the argument of the cinch is very large, the growing exponential part is very, very large. So you can approximate cinch squared as e to the 2x over 4. Right? So when the argument of cinch is very large, then cinch squared of x is e to the 2x over 4. The decaying part is basically irrelevant. E to the minus x is irrelevant. And in that case, you can approximate the tunneling probability. So this is a little addendum, right? So when the argument of the cinch is much larger than 1, which really means that L is much larger than the penetration depth, you can make an approximation so the tunneling probability is given by a simpler, slightly simpler expression. Basically a prefactor, this is called the prefactor, and this is an exponential factor. And I think I'm missing a minus sign. It's very important. Right. So I think in some of the exercises, you can use this simpler expression for the exercises related to alpha decay and nuclear fission. You can use this expression. Okay, and now I will begin discussing the next material. So in 3D, Schrodinger's equation, oops. So actually, let me compare the 1D to 3D. So Schrodinger's equation in 1D versus 3D. So in 1D, it's minus h bar squared over 2m partial squared of the whole wave function. Actually, let me rewrite it like this, like an operator. This operating on the wave function equals minus I h bar, the time derivative of the wave function with respect to time. And this is called Hamiltonian operator. It's made up of a kinetic energy operator, not kinetic energy, but operator, and a potential energy operator, which is just a potential energy. What good is wave function? What good is Schrodinger's equation for? What good is the Schrodinger's equation? Well, it gives you evolution of the wave function. So you start with some initial wave function, some kind of an initial wave function that's psi 0, and the Schrodinger's equation gives you the wave function at a later time. The wave function generally evolves in some way, right? It evolves, might acquire new things, new wiggles, might spread out, and so on. So it really describes the evolution of the wave function. Now, a lot what we've been doing is we've been looking for modal solutions, right? We've been looking for solutions in which the space, in which the spatial we've been looking for solutions that are modal. We've been looking solutions in which you can express as a product of a spatial part and a temporal part. I motivated this when I discussed waves on a string. In general, the motion of the string can be very complicated. If you pluck the string does something very complicated. But you can look for special, very special solutions in which the shape of the string remains the same. And those special solutions are such in which you can separate the spatial coordinates and the temporal coordinates. So these are very special solutions. It's not a general solution. But they're useful because you can build any general solution out of these modes, out of these modal solutions. So these are modes of the Schrödinger's equation. And these modes are solutions that correspond to a constant energy, right? So we spent a lot of time looking for these modes, and these modes are very special wave functions that correspond to a well-defined energy. You can build more general wave functions out of the superposition of these stationary states, a superposition of well-defined energy states. Then if you measure energy, you might get a spread of outcomes distributed according to the coefficients. But that's what we've been doing. We've been looking for these stationary states. I encourage you to look at solutions to the last homework 9, not the last homework, but the homework that you already did, homework 9, and solutions to quiz, to the last quiz as well. Anyway, what about 3D? So if you look at the structure of the Schrödinger's equation, it's kinetic energy operator plus potential energy operator. Operating on the wave function gives minus IH bar times its time derivative. And that remains true in 3D. So in 3D, so if you write this in terms of the operator, right? So this is, I can write this as kinetic energy operator plus potential energy operator operating on the wave function equals IH bar times its time derivative. And the same is true in 3D, the full wave function. But kinetic energy operator is going to be, it's going to involve more than one coordinate. It's a very simple extension. Okay. In fact, there's a momentum operator in the x direction, there's a momentum operator in the y direction, and there's a momentum operator in the z direction. And you can see that kinetic energy operator is just made up of these momentum operators. But if operator, if me mentioning the word operator gives you a headache, I can just say that the Schrödinger's equation in 3D is just written like that. Think of this as just an equation. And u will be a function of x, y, and z. okay? So that's the Schrodinger's equation in 3D. This is pretty cumbersome. This might look pretty scary. So this thing right here, there's a shorthand notation for it. It's called the Laplacian. And it has this funny mathematical symbol. Those of you who took Calc 4, you know what it is. It's just a shorthand. And then the 3D Schrodinger's equation looks less scary. If you write it like that, then it looks less scary. Or you can write this as in an operator form. So it's a Hamiltonian operator operating on the wave function gives the IH bar times the time derivative of the wave function. So this is really the 3D Schrodinger's equation. As before, we will seek modal solutions. Solutions in which the space and time variables separate. So in other words, the wave function is now a function of x, y, z, and t. Is the lowercase a mode as a function of space and some kind of a function of time, a variable separable. So solution, we're looking for very special solutions, in which the spatial and temporal variables separate in this product form. It's not a general solution, it's a very special solution, but the usefulness of them is that in general we can construct any solution out of a linear combination of these modes. And these modes will have well-defined energies as before. So what do we do next? We sub into the Schrodinger's equation and divide it by the big psi. When we do that, we will get the following thing. So these are little psi's, not the full wave function. So as before, this is actually a good review for before. This is a function of time only. And the right-hand side is a function of space, x, y, z, only. The only way that apples can equal to oranges, well, the only way that a function of time can equal to a function of space is if they're both equal to a constant. This is called the separation constant. We use letter E for it because the physical meaning of that constant is energy. Okay? We have exactly the same thing in 1D. And so we end up with a pair of equations, one for the temporal part, which is very simple, with a solution f equals some initial. That's where these temporal coefficients come from. And a separate equation for the spatial part of the wave function, And this is called time independent Schrodinger's equation in 3D. But just as 2D, you can see that you can write this as the Hamiltonian operator operating on the spatial part of the wave function gives you the wave function back multiplied by the energy. So this idea could have been used in doing part B of written quiz 9, but it was definitely not necessary. We discussed this when we talked about 1D quantum mechanics. It might not have stuck. So this is a really good review. In any case, so these are modes of the Schrodinger's equation, and these are energies. And then in general, you can write down any wave function as a superposition with some coefficients. We haven't really done much of that, except that you looked at the superposition of just two modes, two stationary states, two states of well-defined energy. But that's really the importance of these modes. So you can write down the solution to Schrodinger's equation in this form. You don't always have to write it in this form, but one can always express it as a sum of well-defined energy states. It's not always convenient, sometimes it is convenient. And you can see that the wave function definitely depends on time. It evolves in time, evolves in some way as time unfolds. So now, to find these modes, we have to specify the potential energy, right? Because there's a potential energy that's sitting here. So to proceed further, we have to look at each physical situation individually. You know, atom has one, electron interacting with a proton has one potential energy. Diatomic molecule oscillating has another type of potential energy. Proton interacting with the nucleus has another type of potential energy, and so on and so on. And again, we will do this for model potential energies. They don't correspond to anything physically, but they're models that can be very educational, and the outcome of those solutions are also insightful, because a lot of the features of those solutions will carry over to more realistic potential energies. So I've already given you this spiel several times. Well, what do we start with? In 1D, we started with a particle in a box, or infinite well. So potential energy is infinite outside of the well, and it's zero inside the well. Potential energy is infinite outside the well, particle cannot be there, psi is zero there. And inside the well, potential energy is zero, so we can solve the Schrodinger's equation inside the well, and we will apply the boundary conditions that the wave function has to go to zero at the edges. And so now we will do the same thing for a particle in a 3D well. So it literally is a box, right? So 3D infinite well for a particle in a 3D box. As far as I'm used to, all boxes are 3D. So this really is a particle in a box, right? So you have some kind of a three-dimensional box, and U equals infinite outside. Particle can't be there. Psi equals zero there. And by continuity, the psi will also be zero on the edges of the box. And inside, there's no potential energy. Of course, I can always shift. I can say inside U equals 25 joules. It wouldn't change anything as long as you well, it will only increase the values of the E's by the same amount. Remember, you can always change the value of potential energy as long as you do the same thing to the total energy. But why would we do that? It's easier to deal with a U equals 0. And so we really just need to solve the time-independent Schrodinger's equation inside the box and apply the boundary conditions. So potential energy is 0 for x between Lx and 0, y between Ly and 0. It's a parallelepiped. It's not a square box. It's a rectangular box, or in 3D, it's a parallelepiped like this. And so inside the box, you get not too bad. But it's still a little bit bad because x is a function of x, y, and z. So how do you solve this equation? If I can, let me rewrite it. I can rewrite it like this. Laplacian acting on the psi equals minus 2m e over h bar squared times psi. So this is some kind of a constant. I can call it k squared. But how do you solve this, right? This is, you know how to solve this equation in 1D. How do you solve this in 3D? So we will continue separating variables. So I'm going to seek even more special solutions. I'm going to seek modes of this equation. I'm going to seek modal solutions. In other words, I'm going to seek variable separable solutions. I'm going to call it like this. Plug into the time-independent Schrodinger's equation and divide by the wave function. Okay, so plug into time-independent Schrodinger's equation and divide by psi. When you do that, what you get is this is a function of x, this is a function of y. It's stuff that only depends on y. And this is a function of z. It's stuff that only depends on z. And so by now, you will probably agree with me that the only way that you can add function of x and function of y and function of z is and get a constant is if each one is a constant. And so this is equal to a constant. I'm going to call it kx squared. You know what, let me do this. Let me factor out the minus. This is a constant, different constant. It was minus ky squared. And this is a constant. It was minus kz squared. So then we get a triplet of equations. And so we want x, function of x, and then we get similar thing for the y. This produces y as a function of y. Then we get the third equation in variable z, and we want this function of z. Okay? Now these are constants, and then the energy is given by minus, and the energy will be given, so the minus cancel out, so you get h bar squared over 2m kx squared plus ky squared z squared. We will come back to that in a second. And the boundary conditions are x of 0 equals x of lx 0, y of 0 equals y, or y equals 0, and z of 0 equals z of l, z equals 0. Right, so you have the origin, this is your x coordinate, this is lx, this is the y coordinate, this is ly, y, this is lx. And this is LZ. Okay, so I'm only drawing the xy plane. So wave function cannot be 0, and it has to be 0 on these edges, and then here, 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 and on the sides. Okay, so by now you're experts at solving this. You know that you're going to get sines. So you get a times sine kx times x plus b times cosine kx times x. And when we have, well, let me write it down. So for example, a sine kx plus b cosine kxy. But the boundary conditions, b equals 0 because x of 0 equals 0. And kx equals n pi over lx because x of lx equals 0. So you get a sine of kx times lx equals 0. So either a is 0, then you don't have a wave function at all, or kx lx equals n pi. And that's how you get this solution. So in summary, what we have is we have x of x equals sine mx. I'm going to call this mx. What's going on here? Yeah, so I'm going to call this index nx. So you get your general solution, and similar thing for the y parts. And similar thing for the z part. And the energy of such, so this is a mode. So this is a, let me first write down the energy. Kx squared plus ky squared kz squared, which is equal to h bar squared over 2m pi squared mx squared over lx squared plus y squared over y squared plus nz squared over z squared. So you get modes each characterized by a triplet of numbers nx, ny, and nz. So for example, a mode with nx equals 5 and y equals 3 and nz equals 1, I can call it 5, 3, 1 mode. It's a function of x, y, and z. And it would be what? It would be 5 pi over Lx x times sine of 3 pi over Ly y times sine of pi over Lz z, and it has energy, this mode has energy h bar squared pi squared over 2m 5 squared over Lx squared plus 3 squared over Ly squared plus 1 squared for Lz squared, right? And the most general solution is a sum over all possible modes. So let me not go there right now. Anyway, you get modes, and each mode is characterized by these integers. These integers, nx, ny, and nz, are called quantum numbers. In general, if you have a modal solution, if you have a solution, it's characterized by a set of quantum numbers. If you specify all the quantum numbers, you specify the solution. So like what I did here, I said, give me a solution with quantum numbers and x equals 5 and y equals 3 and z equals 1. When I specified those quantum numbers, I specified a particular mode, a particular solution that has a particular value of energy. The next thing that I should mention is what your book mentions, is called degeneracy. So note that you can have the same value of energy for different modes. That generally the same value of energy is shared by multiple modes. So for example, the 1, 3, 1 mode, the 3, 1, 1, no, I guess I should say, no, let me keep saying this, mode, and 1, 1, 3 mode will have the same energy if Lx equals Ly equals Lz. So if you look at the energy equation, if all the L's are the same, right, so then you have h bar squared pi squared over 2m L squared, and you get nx squared plus ny squared plus nz squared, and you get the same number for 1, 3, 1 solution, or for 3, 1, 1 solution, or 1, 1, 3 solution. So this is the key. If the lengths are the same, then these solutions will have the same energy. If the lengths are not the same, these three solutions will have different energies. So why is that? So first of all, this situation when multiple solutions or multiple modes have the same energy is called degeneracy. Okay, multiple solutions have the same energies. And in general, it is not an accident, but it is related to the symmetry. So when we made the box a square box, we made it more symmetrical. We ended up with having multiple solutions that have the same energy. So to drive this point home, consider a square box. I'm going to do this in 2D. And let's say you have a 1-2 mode and a 2-1 mode. So 1-2 mode means you have only one antinode in the x direction, but in the y direction you have two antinodes. So it's kind of hard to visualize these things. But let me see if I can try to depict. So you have, yeah, imagine if this is like a square drum. It has only one lobe in the x direction, but in the y direction it's positive and negative. It's hard to visualize. If you look at such a drum from the top, so top view. So this is your drum. And what it will be, this will be depressed and this will be up. And on the other hand, this mode, the 1-2 mode, it will be, for example, like this. And so this drum will oscillate. So the 1-2 mode will oscillate like this, and the 2 mode will oscillate like that. So let's say you have a drum, the first one, and it oscillates like that, and it oscillates with certain frequency. In quantum mechanics, you don't have a drum, you have a particle in the box, and it has a certain energy. But the difference between these two drums is not physical. All you have to do is you just have to turn your head like this, and then drum 1 becomes drum 2. So clearly, it has to have the same energy. Because the drum is symmetric, there cannot be a difference in the energy between this kind of mode and this kind of mode, between the 1-2 mode and the 2-1 mode. Because really the difference between the 1-2 mode and 2-1 mode is you turning your head like that. And certainly energy cannot depend on your coordinate system, which is what turning the head really means. So whenever you have symmetry, generally you will have more than one mode, more than one solution sharing the same physical property like frequency or energy. So degeneracy is usually a consequence of symmetry. So this is an important idea. I can also, it's usually a consequence of symmetry. Sometimes sometimes you get degeneracy, you get two states, two modes, two solutions, two stationary states, two wave functions with well-defined energy that have the same energy, but not because of symmetry. So that's called accidental degeneracy. But typically degeneracy is related to symmetry. You can ask, what is the degree of the degeneracy? So for example, in 2 dimensions, if I have the degree of degeneracy just refers to how many states have the same energy. So if I have 1, 2 mode, so this will give me 1 squared plus 2 squared, so that's equal to 5 times the constants. And I have mode 2, 1, so it gives me 2 squared plus 1 squared equals to 5. So this will have the energy times 5. I can ask, how many states have this energy? The answer is 2. These are the 1, 2 states and the 2, 1 state. The 1, 2 state and the 2, 1 state. So the degree of degeneracy equals 2. Okay, so the degeneracy of degree 2. In 3D, the degree of degeneracy will increase because there is more symmetry, right? You can have a mode like this and a mode like this and a mode like this that all have the same energy, because really the modes only differ by rotating coordinates. The one mode can be transformed into the other mode just by rotating the coordinate system, and energy cannot possibly depend on our coordinate system. Your textbook lists energies of the first, I don't know, 20 or so modes, maybe more. And so you have only one mode, 1, 1, 1. You have so the next energy, that's 6 times a bunch of constants. There are 3 of those, the 2, 1, 1, 1, 2, 1, and 1, 1, 2. The next value of energy has a trifold degeneracy, 1, 2, 2, 2, 1, 2, and 2, 2, 1. The next energy, or value 11 times a bunch of constants, has also trifold degeneracy, 3, 1, 1, 1, 3, 1, 1, 1, 3. The next is non-degenerate, 2, 2, 2 is non-degenerate. Then the next one has 6-fold degeneracy, 1, 2, 3, 2, 1, 3, 1, 3, 2, 2, 3, 1, 3, 1, 2, 3, 2, 1. And the energy is 14 times a bunch of those constants, and so on. One thing I could add is you could represent a possibility of states. I'm going to do this in 2D in the following way. So this is your space of the indices, the space of quantum numbers. This is 1, 2, 3, 1, 2, 3. And you could sort of represent modes graphically. You have a lattice of these values of n, these quantum numbers. So this one, for example, is a mode, and x equals 4 and y equals 2. And since energy is proportional to nx squared plus ny squared, and this is like a radius, right? So you can have situation when more than one point lies on the surface of constant energy. So that's how you can represent the degeneracy. So for example, like this, or something like this. So here's the second energy, the first energy level has no degeneracy, but the second energy level has a twofold degeneracy. So this is in 2D, and in 3D, these are surfaces of a sphere, and the surface of a sphere will generally go through more points. So in 3D, you have a higher fold degeneracy. Degeneracy is important. So notice I said that if we have a square box, the second energy level will have a bifold degeneracy. Let's say your kid sister comes and kicks your box. Let's say you have a musical instrument that looks like this. It's a drum, and this mode of the drum and this mode of the drum have exactly the same frequency. Your kid sister is angry at you, she kicks and she changes the drum. Now it's no longer symmetric. And that splits the degeneracy. So let's say I can look at, this is the energy, and I fix Lx and I vary Ly. So when Ly equals to Lx, you have a bifold degeneracy, but when you make Ly different than Lx, you lift the degeneracy. And so now it's no longer true that both this mode and this mode have the same energy. Because remember that energy is proportional to nx squared over Lx squared plus ny squared over Ly squared. So now the 2, 1 and the 1, 2 states no longer have the same energy. And the more the L's differ from each other, the greater is the energy difference. And this again is just showing that you get degeneracy. Degeneracy is usually a consequence of symmetry. When you make something less symmetric, you lift the degeneracy and you split the degenerate. Split the degenerate. You split the degeneracy. That's what you do. Okay. So this idea of degeneracy, it applies to other things. It permeates to other more mature problems. We see it in the particle in the three-dimensional box, but it's one of those things that we use a simple model to learn something, and then it turns out that this idea of degeneracy being related to symmetry and splitting the degeneracy by making things less symmetric, that carries over to other more mature problems. Okay, so that's the particle in three-dimensional box. You're gonna get a bunch of exercises in the homework. If you like the book's presentation, maybe that will complement my presentation. We discuss exactly the same thing. So that's your particle in the box, and then we'll move on to other problems tomorrow. Thanks.